is not 100% pure, which means that it contains the chemical and it also contains impurities in that. So for example, when we are looking at water, tap water, so tap water contains water, but it will also contains chlorine, bacteria, other like ions and other chemicals depending on what it has been treated with. So it's not 100% water. So when we're looking at an impure substance, we cannot use MR, we cannot count number of moles of an impure substance because the MR is not going to be equal to the MR of that compound. So for example, water, pure water has MR of 18 gram per mole, but impure water will have an MR value which is more than 18 gram per mole because it contains impurities. So we don't know the MR of an impure substance. So whenever we have an impure substance, we cannot use number of moles is equal to mass over MR. For impure, it doesn't work. So for impure substances, it doesn't work. This only works for pure substances. So when you know that, yes, this substance contains only this pure compound. So percentage purity is the mass of the impure substance, is the mass of the pure substance over the mass of the total substance which is impure. So how much pure substance do you have over the total sample which is impure? Times 100. So that would be a percentage purity. So let's see the first example. A chemist made 60 grams of aspirin and analysis showed that it contains 1.5 grams of impurities. So you need to find the purity of the aspirin sample. So 60 grams of aspirin, this is the total mass of sample, total sample, and that sample is impure. And analysis has shown that it contains 1.5 grams of impurities. So what is the mass of pure substance then? So pure aspirin would be 60 minus 1.5. And the mass of the impure substance, this is the total sample, and so the percentage purity would be the pure sample, mass of pure sample over the total times 100, and that gives me a percentage of 97.5. Now let's see the second example, which is a bit different from the first one. Here we have impure copper which was heated in oxygen to form copper oxide. So that's the equation. Impure, this is impure. And this impure substances, so let's say I have that sample of copper. Let's say whatever is in red here is pure copper and the other remaining space is impurities. So this is impurities. The blank is impurities. And the red part is pure copper. But we don't know how much is pure, we don't know how much is impure. So when we burn this in oxygen, let's say we are reacting this with oxygen, what is going to react? It's only the pure copper. So whatever is the pure copper will react with oxygen to give us copper oxide. Now this copper oxide that we're going to get is going to be pure because it's only the pure copper that is reacting with oxygen. So this product here, the product obtained is going to be a pure substance. Now from the amount of moles of copper, I can get the amount of moles of pure copper in that sample. Okay, let's do this. So I have 3.2 grams of copper oxide which was obtained. So number of moles of copper oxide would be mass of copper oxide divided by the MR. So copper oxide is 80. So 3.2 divided by 80. So this is the number of moles of copper oxide. Now this copper oxide is coming from the copper. So from the equation, copper oxide is coming from copper. So I'm going to look at the mole ratio. And this is 2:2. Therefore, it's 1:1. Okay, so if I have 0.04 moles of copper oxide, this is coming from 0.04 moles of copper, which means that in that impure sample, I have only 0.04 moles of copper. So this represents what mass of copper? So mass of copper would be number of moles times mR. Because this is pure, we can use number of moles times mR. And this gives me 2.56 grams, which means that pure copper is 2.56 grams and the impure sample is 4.3 grams. So the impure sample, this is 4.3 grams. Therefore, the percentage purity is calculated by the mass of the pure sample divided by the mass of the total sample, which is impure, times 100. That gives you 59.5%. And this is the percentage purity of the copper sample. Okay. Now let's see percentage yield. Now when we're doing an experiment, let's say we have hydrochloric acid and then we are adding calcium carbonate in that, and we are investigating how much carbon dioxide is being produced in that experiment. Excuse the diagram. Okay, you get the idea. So this is going to give off carbon dioxide gas, which is going to be collected in this gas syringe over here. Now, depending on how much hydrochloric acid and calcium carbonate we use, we are going to expect a certain amount of carbon dioxide. Let's say from the equation and using the number of moles and using the mole ratio, we get, let's say, 24, let's say we're supposed to get 24 centimeter cube of gas. But when you do the experiment, when we're using the calcium carbonate, so calcium carbonate has some impurities in it. When you get the calcium carbonate, there is some impurities in it. And also when you're reacting it, because there's a lot of effervescence over here, there might be some, because there's lots of effervescence, there might be some liquid or some acid that gets trapped on the corners of the conical flask, which means that not all of the acid or not all of the calcium carbonate reacts, which means that even in theory, this is what we expect in theory. But when we do the experiment in practice, we are going to get less than what we expect in theory. So this is where percentage yield comes in. So percentage yield is the actual amount of product that you get over the theoretical amount of product that you were expecting to get from theory. So you see theoretical mass, which means, so in theory, using the mole ratio, using the equation, this is what you're expecting to get in theory. So percentage yield, you can do it either using mass, so actual mass over theoretical mass, or you could use volume, which is actual volume divided by theoretical volume, so mass or volume, or you could use number of moles, actual number of moles that you're getting over theoretical number of moles of the product. So let's see the first example. So a student reacts 9 grams of aluminium powder with excess chlorine. So the amount of chlorine is in excess, so we don't really need to know the number of moles of chlorine because it's in excess. which means that aluminium is going to be the limiting reagent. The mass of aluminium chloride is this, so calculate the percentage yield of aluminium chloride. If you need to find the percentage yield of aluminium chloride, means that you need the actual mass of aluminium chloride. Let's work in mass because the mass is already given here. So actual mass of aluminium chloride of AlCl3, and you need the theoretical mass of aluminium chloride. You need these two values. So here in the question, you are given that the mass of aluminium chloride produced is this. So from what we are given, this here is the actual mass. So when you do the reaction, this is what is produced. So this is the actual mass. We know this. The theoretical mass, we need to find it. So how do we find it? First, we'll start with the equation. Aluminium reacts with chlorine to give you aluminium chloride. So balance the equation here. Now, you know that 9 grams of aluminium powder was used. So number of moles of aluminium used, number of moles is mass divided by AR in this case. So 9 divided by 27. Here. Now from the mole ratio, aluminium is to aluminium chloride. So this is 2:2, which means it's 1:1. Okay, so if we have 0.33 moles of aluminium, means it will react with 0.33 moles of aluminium chloride. So using the MR of aluminium chloride, we can get the mass, the theoretical mass of aluminium chloride. So mass is number of moles times MR, which is going to be 0.33 times the MR of aluminium chloride. So this is the theoretical mass. Then the percentage yield would be the actual mass over the theoretical mass times 100. So for this reaction, the percentage yield is percent. Okay, and percentage yield, make sure that you're going to multiply by 100. So it's a percentage. Okay, so try to complete these parse exam paper questions.